Good evening, everyone. Welcome to Pace Law School. For those of you who don't know me, I'm Jason Zarneski. I'm the Kurland Distinguished Professor of Environmental Law and Executive Director of the Environmental Program here at the Law School. This is really a wonderful event that we have this evening. We're, of course, extremely excited to have Michael Oppenheimer speak this evening. And it's also an exciting event as we continue to work with the other environmental programs at Pace University. Not only do we have a wonderful environmental program here at the law school, but we have a new Department of Environmental Science and Studies at the university, and we also have our Pace Academy of Applied Environmental Studies. And so I'm just here to welcome everyone and to introduce Michelle Land, who's the director of the Pace Academy and also a graduate of the law school, and she'll be introducing Michael Oppenheimer. So, Michelle?
Good evening, everyone. As Jason mentioned, my name is Michelle Land. I direct Pace Academy for Applied Environmental Studies. For those of you who that is new to, Pace Academy is a university-wide center for excellence. And among the things we do are work across the 6 schools and colleges at the university, such as working with students and faculty, collaborating on an undergraduate environmental policy clinic, which has multidisciplinary teams of students working with clients externally on policy research, design, and implementation. And another program that you are all benefiting from today is our Visiting Fellow program. We have every year, we invite an expert to Pace Academy to serve as a resident for a week. We are so fortunate to have Dr. Michael Oppenheimer accepting our invitation for this year's Pace Academy Visiting Fellow. He is an internationally renowned climate change scientist, policy maven, and an exceedingly clear communicator of all things climate related. His willingness to join us fresh off the road from his travel to Copenhagen, where the International Panel on Climate Change, as you'll soon learn, IPCC, released its 5th assessment report. It's a very exciting opportunity to hear Dr. Oppenheimer's firsthand account of the writing of the report and his predicted political fallout of its release. Dr. Michael Oppenheimer is a longtime participant in the International Panel on Climate Change, which won the Nobel Peace Prize in 2007. He served as lead author of the IPCC's 4th assessment report, and recently as a coordinating lead author of the 5th assessment report and a special report on climate extremes and disasters. His work on this issue dates back to the 1980s, when Dr. Oppenheimer and a handful of other scientists organized 2 workshops under the auspices of the United Nations that helped precipitate the negotiations, that resulted in the United Nations Framework Convention on Climate Change, which was signed at the 1992 Earth Summit, and the Kyoto Protocol. During that period, he co-founded the Climate Action Network. Dr. Oppenheimer is the Albert G. Milbank Professor of Geosciences and the International Affairs in the Woodrow Wilson School and the Department of Geosciences at Princeton University. He is also the director of the program in Science, Technology, and Environmental Policy at Woodrow Wilson School. He's a faculty associate of the Atmospheric and Ocean Sciences program, Princeton Environmental Institute, and the Princeton Institute for International and Regional Studies. Dr. Oppenheimer joined the Princeton faculty after more than 2 decades with the Environmental Defense Fund, where he served as chief scientist and manager of the Climate and Air program. And he continues to serve as a science advisor to EDF. He has been a member of several panels on the National Academy of Sciences and is now a member of the National Academy's Board on Energy and Environmental Studies. Dr. Oppenheimer is a 2010 winner of the prestigious Heinz Award and a fellow of the American Association for the Advancement of Science. His research and advocacy work on acid rain also contributed to the passage of the 1990 amendments of the Clean Air Act. Dr. Oppenheimer has been a guest on many television and radio programs, including ABC's This Week, Nightline, Alcove, The News Hour, The Oprah Winfrey Show, Charlie Rose, ABC News, and of course our favorite, The Colbert Report. Prior to his position at the Environmental Defense Fund, Dr. Oppenheimer served as atomic and molecular astrophysicist at the Harvard Smithsonian Center for Astrophysics and lecturer on astronomy at Harvard University. He received his SB in chemistry from MIT and a PhD in chemical physics from the University of Chicago, and pursued postdoctoral research at the Harvard Smithsonian Center for Astrophysics. Please help me in welcoming Dr. Michael Oppenheimer.
It's a great pleasure to be here. I haven't been up here in a few years. And I've spent most of my career trying to turn science into some practical use, and particularly around the environment. So I'm particularly honored to be at a place where you started the Pace Law Clinic, because I, of course, knew the people who started, still know the people who started, and it's a great model for how you can put wheels on the law and make it useful in terms of helping people solve problems where they live, and it sort of closes the gap between what most people regard as something sort of esoteric going on up here and the problems they actually live with at ground level. And it's sort of with that in mind that I got involved with the Intergovernmental Panel on Climate Change, which was established in 1988 under the UN auspices. It's a vehicle for informing governments on what the real science of climate change is all about, and it's become very influential because all governments, no matter what the static you hear in the press, listen to what the IPCC says about what the state of the science is. They may not act on it. In fact, what they do almost always falls short of what they should do in the scientist's view. But nevertheless, it's important to know that they're all on the same page. They can't claim that they don't know what the problem is. They can't claim they're not acting out of ignorance. If they don't act on this problem, it's for other political reasons. Now, somebody's going to have to show me how to advance things, or do I just signal somebody? Or do I touch this? I mean, what's the clicker right here? I don't want to cause problems. Okay, all right. So I'm going to talk about, I'm just going to use the recent IPCC report as scaffolding to talk more generally about the climate change issue. And I'm going to run through very quickly a basic introduction to the issue, and then move on the science side, and then move towards what people are thinking about whether it can actually be solved and at what level. And the key thing here is, look, climate is already changing. We've pumped up these gases called the greenhouse gas. We've been doing it for almost 200 years now, product largely of industrialization. We know these gases are transparent to sunlight, which warms Earth's surface, but that they trap heat that would otherwise escape into space. And that's a good thing naturally. There are a lot of greenhouse gases in the atmosphere naturally, because without it, Earth would be 60 degrees Fahrenheit colder than it is today, and this would be a frozen desert. I wouldn't be here talking to you because human beings would not have evolved. The greenhouse problem arises because human beings are increasing the natural level of these gases in the atmosphere, primarily by burning fossil fuels, coal, oil, and natural gas, which is turned into carbon dioxide. And it's created what I think is the major problem, other than people going to war with each other, which seems to never go away, for the 21st century. And the problem isn't just the science problem itself or figuring out what to do about it. Governments have some very good ideas about what to do about it. The problem is represented by this, which is basically the story about how too often governments manage risk. On the left-hand side, you see the risk is perceived. In the middle, they assess the risk. They kind of talk to each other about what to do about it. But by the time they decide what to do about it, well, they have to basically run for their lives. That's us. That's not just them. Because they're, too frequently a step too late. With this problem, we're already late, but not quite too late. And that's where I get to the issue of danger. Danger isn't just a general concept with climate change. It has a particular legal definition. There's one treaty that the U.S. actually signed on climate change. It's called the UN Framework Convention on Climate Change, signed at the Rio Earth Summit in 1992. We are legally bound to do what we said we would do under that convention. And what's called Article 2 of the Convention states that its long-term objective is to prevent, quote, dangerous anthropogenic, man-made, human-made interference with the climate system. And for 20 some odd years, there's been a lot of work in the scientific community, in the political community, in the legal community, to try to figure out what that means. What does it mean for climate actually to be dangerous? And I'm going to talk a little bit about that today, show you how close we are to what scientists and governments think is the danger point, and then talk about how we can pull back from the edge. So how do we know this stuff is actually the reality? Well, you'll see in back of me data on what carbon dioxide levels have been in the atmosphere over the last 10,000 years. The 0 on the right is today. The 10,000 on the left is what the levels were 10,000 years ago. How do we know this? Because scientists go to Antarctica and Greenland, where we have big ice sheets. They drill under the surface of the ice. They pull up the ice. The ice has bubbles in it, air bubbles. Those air bubbles are samples of the atmosphere from the time the snow fell that formed the ice. It got trapped, and in most respects, it is unchanged. And this archive of the natural history of the atmosphere goes back 800,000 years. In fact, there's a 1,000,000-year-old chunk of ice they've recently discovered. They just haven't analyzed it yet. So this comes from the top 10,000 years of those ice cores, and you can see sort of the vertical rocket ship on the far right. That's the rise of carbon dioxide when basically the Industrial Revolution starts. So you can see in the inset on the upper left, so it's a slightly different scale, that's the carbon dioxide levels since 1800, and you notice there's this very continuous upward tick, so that carbon dioxide is now 43% above what it was before industrialization. That has to have effects on the Earth. The basic physics of the problem tells us it has to have effects because it means we're trapping more heat and we are inevitably warming the Earth. And the most dangerous part of it is that this is different than every other pollution problem that we know of, almost every other. And that's because the atmosphere behaves a lot like a bathtub, and the emissions of carbon dioxide from burning coal, say, are a lot like the water that flows from a faucet into the tub. Only the trouble with this tub is the drain is sort of clogged. The carbon dioxide is removed only very slowly from the system, mostly by dissolving in the ocean water, but that's a very slow process. So that if you have a very clogged drain and you have exponentially increasing emissions over time, which is what we've had, it's inevitable the level is going to increase. If your aim is to stabilize that level and eventually let it decrease, stabilize the level before it gets dangerous, that is, and the level is the amount of carbon dioxide which brings a certain level of climate change, and you want to stabilize it before it reaches a dangerous level and then kind of pull the plug on it and let the excess carbon dioxide drain out, that turns out to be a very slow process. Some of the carbon dioxide we emit today will still be in the atmosphere, about 25% of it, 1,000 years from now. That's a millennium. The only way that stuff gets out of the atmosphere is if some genius invents a cheap and widely available way to vacuum the atmosphere. And there are ideas on how to do that, but they're incredibly expensive. Who knows? 150, 200 years may happen, but not in our lifetimes and probably not in your children's lifetimes. So we have to, and even if it is, it's a big risk to assume it's going to happen. So that is this vacuum cleaner effect. And so we have to act for all practical purposes. Like the gases we're putting up in the atmosphere today are there for a very, very long time. And that's what the chart on the upper right shows you. If you let carbon dioxide grow with a business as usual growth of 2% per year until the year 2100, and then you stop the growth, you just shut off the experiment, you'll start at that peak around 1,200 parts per million, and then it'll go down, but you notice 1,000 years from now, there's still 800 parts per million of carbon dioxide in the atmosphere when the normal pre-industrial level is 280. So we're way out of whack, and we have to slow it down and eventually turn it around, but it's very hard to walk backwards because, again, it has this long lifetime. Now, fossil fuels are largely responsible, as I said, but there are other greenhouse gases, particularly The upper panel shows the levels of the growth of the three greenhouse gases in the atmosphere. The green is carbon dioxide, the yellow is methane, the major component of natural gas, which reminds us that in the rush to natural gas, if we're going to use it, you have to not lose it. You have to make those systems leak tight, and they are far from leak tight today. And the lower curve is nitrous oxide, which is a product of various kinds of bacterial degeneration, but also produced to some extent by fossil fuel burning and is aggravated by agriculture and sewage outfalls from which nitrous oxide is released. But the biggest problem is carbon dioxide, and the lower panel shows you the growth of fossil fuel use, which is the gray part, and carbon dioxide from cutting and burning of forests, deforestation primarily in the tropics, which is the amber or yellow curve at the bottom. And the interesting thing to note, when I got into this problem too long ago, in the early 1980s, the contribution from deforestation was about 25% of the contribution of fossil fuel combustion. But deforestation has mercifully slowed a bit, largely by a change in management of the forests in Brazil. It's not a war that's won permanently, but for the time being at least, their emissions have slowed, while we've had this tremendous growth in coal burning in China, India, and many other developing countries. So that's why you see these two curves separating. And just to show you what the numbers look like, most of the biggest source of greenhouse gases into the atmosphere is from the energy sector. That's power plants. So when you see that smoke balloon there on the left, that's electric power production. The next one, again, is deforestation. When you go, but not just deforestation, but also these emissions from agricultural soils, which includes methane and nitrous oxide. The third one is industry, just direct burning of fuel to power factories. Then transport, cars, buses, airplanes, et cetera. And finally, heating buildings. And you can see you're not going to solve this problem unless you tackle the electric power production source and the source from forests and agriculture. So all this stuff going into the atmosphere, as I said, the physics says it has to have changed the climate, and it has. The upper curve is Earth's temperature since 1850. What was special about 1850? That's about the time that there were enough reliable thermometers around Earth's surface so that scientists 100 years later could pick up the data, analyze it, and get a convincing picture of what Earth's temperature was on a global average basis. And you notice the curves has a lot of bumps in it. Some of those bumps are natural variations in the climate, which sometimes the climate will be a little warmer than average over one decade, then a little cooler than average the next decade. This is because energy flows between the atmosphere and the ocean, and it doesn't only stay in the atmosphere, and that variability affects the long-term average temperature of the atmosphere. Then during some periods, for instance, around 1940 to 1970, you'll see a flattening of the curve. That's believed to be because coal burning came on very fast in the period after World War II, and that for electric power production uses. And coal burning emits a lot of particulate. Before the U.S. Clean Air Act and the European actions on clean air started around 1970, the particulates were reflecting a lot of sunlight, and that offset some of the global warming. But then warming resumed rapidly, and if you move to the right side of the curve, you see a very fast warming followed by, again, a little bit of a flattening. That flattening is sometimes called the warming hiatus, and the contrarians and some poorly intended political leaders have used it as an excuse to say, well, Earth isn't warming, hasn't warmed in the last 16 years. But if you look against the background of all the other oscillations in the curve, it fades into insignificance. And we also now understand why it happened. It has to do with this movement of energy from the atmosphere to the ocean. And that means it's going to pop out again eventually, and we'll start a rapid warming again, probably within anywhere between 0 and 10 or 15 years. By the way, it's not like there's been zero warming over the last 15 years. It's been slower than the previous period. And there have been some very remarkable consequences of that warming. We're seeing much more extreme heat. we're seeing in some places more extreme drought. And worldwide, almost, we're seeing an increase in sea levels. Why do sea levels change when the Earth warms? Fluids expand when they're heated, so the water in the ocean takes up more volume. And mountain glaciers melt, so there's more water in the ocean. That's happening worldwide. And the two ice sheets, the major ice sheets in Greenland and Antarctica, are both frittering away, particularly at their peripheries, adding water to the ocean. And that's a big problem because those ice sheets contain about 200 feet worth of sea level rise. Most of it will not go into the ocean during this century or even the next century or the century after, but enough is starting to leak out, so it promises a big momentum of growth in sea level. So how much has sea level actually risen? It rose about 8 inches over the past century, and that's already added to problems of erosion and submergence and protection of infrastructure along the coast. And it may not sound like a lot, but for every foot, 8 inches, close to a foot, 2/3 of a foot, for every foot vertically that sea level rises, it takes away 100 feet horizontally through erosion and submergence on a typical East Coast beach. That's a major reason why we're having troubles along the coast. Then when a storm comes, the storms push the water in further, and you get flooding to areas that it never happened before. That was part of the lesson of the recent big hurricanes like Hurricane Sandy. Now, why should you believe all this? Certainly not just because someone with a degree stands up in front of you and tells you so. There's actually firm evidence that this is happening. There are many different bits of evidence. I'll just show you 2 of them. The easiest to understand is probably the right-hand figure. What this does, it's a little small. Can you see it? You see it well enough? If you don't, that's too bad. I can't do much about it at this point. I have this, I have a rule in my head, 1 slide per minute. And so, but all that's done is force me to take 2 slides and put the information from what used to be 2 slides into 1. It's totally self-defeating. But what this is the way the black curve on each of the little squares is the temperature of area of the globe: North Pacific, North Africa, Arctic, Europe. You can see everywhere that the observed temperature in each continent, not just the global average temperature, has increased over the past 100 years. Each of these little squares goes from 1910 to 2010. That's the scale on the bottom. And the pink around the black is what do models project, the computer simulations of the climate. What do they say about what the temperature change should have been, given that the greenhouse gases have increased? If the 2 things don't match up, it means there's something wrong with our models, and we can't use them to project the future with any credibility. If the 2 things line up pretty well, within the uncertainty, we don't know exactly how much each molecule of carbon dioxide going into the atmosphere will affect the climate. We have a pretty good idea, plus or minus 50% in temperature, less than that now. And you'll see continent by continent that there's a very good match between the black curve and the pink bar, the pink field of uncertainty. The purple below the pink asks the following question: if you took the greenhouse gases out of the model and you pretend that you leave them in there, but you pretend they didn't increase over the past century, that carbon dioxide wasn't 43% higher now than in pre-industrial times, what climate would you predict? And you see continent by continent, you get the wrong answer, with only one exception being Antarctica, where there hasn't been as much warming as other continents simply because there's a very big, cold ocean around it, which has a lot of inertia. So we feel pretty confident in these models for, again, several reasons. One of them is it reproduces the past temperature change. Therefore, within reason, within a few degrees, we think it could do the temperature change we're pushing into the system for the future. Another reason is the left-hand panel, which shows you the thing to focus on there is the black, which is Earth's temperature, and the the gray curve at the bottom, which is essentially carbon dioxide in the atmosphere. Before humans started interfering with the system, temperatures on Earth varied a lot because the Earth's orbit change, and these little changes in Earth's orbit would change the amount of sunlight hitting on Earth, which would add a little bit of warming, but it would also change, for instance, the amount of biological stuff growing on the surface. That changes the uptake of carbon dioxide in photosynthesis, and this changed the amount of carbon dioxide in the atmosphere. There are also other processes that were sensitive to this change in sunlight. And you can see over the last, in this case, it's 700,000 years, the whole history of that ice core archive, that there's been a very strong correlation between temperature changing and greenhouse gases changing. So we know these things have always tracked with each other, at least over the last 800,000 years. We have earlier evidence which shows a similar relationship. We know that our models say the warming has started to happen, and that we know the warming started to happen. We know the models say the amount of warming we're getting is consistent with the behavior of carbon dioxide as a heat trapper. It makes sense to believe that that's what's going to happen in the future. And as I said, this is just two of many pieces of evidence. Now this isn't just a matter of thermometer readings. The Earth has changed in some respects quite remarkably, particularly at the high northern latitudes, the Arctic. And we're starting to see more subtle changes on every continent. This is my favorite picture from the IPCC report for two reasons. First of all, it's unintelligible, so I like to show it. And even if you look close up, it's just a good object lesson in why scientists are, the fact that scientists are not very good communicators. But the other point about it that I like is when part of the IPCC process is our report is presented by governments to governments, and it's really like a negotiation. The governments have to accept, in particular, the summary we present of the report. And when this was presented, actually, each country in each continent was shown. It was divided up, and the continents and the symbols which represent impacts like slowdown in crop productivity, loss of fisheries, health effects due to excess heat waves, loss of glacial ice. There was a line from each of these icons onto some point in the continent which showed some country the loss was associated with. But because this is a political process in the end, countries started complaining that we weren't showing the impacts for their country. But of course it was impossible to squeeze for 190 countries, even one icon per country on the map. So the political compromise was just show it as a continental average. Don't show what goes on in individual countries. Don't try to locate them. That's the kind of, you could either view it as political wisdom of the representatives there, or fun and games that goes on at these conferences that I have spent too much of my time on. In any event, the point of this is just get the impression that there are widespread impacts of climate change already worldwide. And just to show you one of them, I was on my way from Malaysia last spring, coming back from one of these IPCC meetings, and the plane flew right over the pole. And I kept my eye on the map, on that you can follow the flight path on. And luckily, it was clear as a bell when we flew close to the pole. It wasn't right over the pole. And I was looking at my window. This is early July. There should still be a solid, 50 years ago, there would have been a solid pack of ice there, except some ice breaking up here and there. But you look at this, the thing is just fragmented already. So this is symptomatic of the long-term downward trend in the Arctic ice pack, and it is by and large due to global warming. Wait a minute. Whoops. Now I'm going to have to try to get back. I got back. So that's as of today. Now let's look at the future. The upper curve tells us it's the projection from the computer climate models of how warm it's going to get. The left-hand axis is degrees Celsius. So if you want it in Fahrenheit, you multiply it by 1.8, close to 2. And the colors are there are two different emissions trajectories for the world shown here. The lower color, the blue color, says we do everything we can plausibly do as soon as possible to cut emissions. And we have a chance for Earth's temperature to sort of maximize somewhat short of the 2 degrees Celsius or about 3.5 degrees Fahrenheit warming, which the governments themselves, based on the scientific evidence, have said is the danger point. Above that warming, the risks, it's not like the Earth all of a sudden starts burning and explodes if we get 2 degrees Celsius warmer. It's that the risks pile up in an unacceptable way. I'll show you that later. And so that's the blue curve is if we do our best efforts. That's what's believed the best efforts look like. The upper curve, the orange, is sort of business as usual. We don't know really what would happen. It's hard to project emissions. You have to figure out what people are going to be driving or flying or heating their homes with 50 and 100 years from now. Maybe everybody's got an individual personal levitation device. Is your levitation device going to be solar powered? I wouldn't trust that because like that thing that landed on the comet, if it gets oriented badly, the solar power goes out and you drop to like a stone. So there's probably going to be fossil fuels in that, maybe biofuels, who knows. And then the band around each projection is the uncertainty because we don't feel entirely confident that we know how the atmosphere responds. This is called climate sensitivity. So those are the two big uncertainties. What are future emissions and how sensitive is the climate? But putting those details aside, business as usual makes us somewhere between 3 and almost 6 degrees warmer than today. And if you want to ask yourself what that's like, Earth hasn't been that warm in probably tens of millions of years. When dinosaurs were just started to be dominant, so the Earth might have been a little warmer than 6 Celsius warmer, more in the 7 to 12 range. But we would be remaking Earth to be totally different than anything you're familiar with, both from a climate point of view and then the responses in the human system and the natural system to that climate change. And similarly, in the bottom panel, you see the sea level for the 2 sets of projections. Even in the low, we do all our best efforts. Oh, by the way, the blue curve, the temperature change in the blue curve would be a bigger temperature change that has happened and faster than in the entire history of civilization. And we don't know how well we'll be able to respond to that. It won't eliminate humanity, but it's going to create a lot of difficulties, even at the low end. Same for sea level rise. Even at the low end, the sea level rise is 50% faster than what we've had in the past 100 years, which, as I said, has caused some problems. And at the high end, it's just hard to know how we would adjust. We're talking about a meter, about 3 feet of sea level rise in the high scenario. And again, think of that as on a typical East Coast beach, 300 feet disappearing permanently. And this is what it looks like if you just color it and smear it around the globe. The upper panel is the temperature change. The left-hand globe is the low emission scenario. The right-hand globe is the high emission scenario. And you just notice that the high emission scenario, we're talking about temperature changes in the range of 5, 7, 9, 10 degrees Celsius. So double that to get Fahrenheit. And you notice particularly in the Arctic, it's just, we'll remake the Arctic completely, and even in places like the mid-continental areas of the United States and Eurasia, which tend to, North America and Eurasia, which tend to warm faster than the global average, we can see remarkable changes on the order of 4, 5, 6 degrees by the end of the century that we live in. The lower panel is precipitation changes. The most notable thing about that is the brown areas, which shows drying, and what it shows is some of the areas which are ready or are relatively poor and have sporadic, perpetual malnutrition and sporadic starvation are going to be victimized by not only more heat, but more drought, which is bad for agricultural productivity. Now, when you think about what to do about all this, keep in mind, it's not just a story about these physical changes. It's not just a story about temperature change. It's not just a story about sea level rise. It's not even just a story about more storms and how bad they are. It's a story about risk to people and infrastructure and ecosystems. And risk isn't just a physical change, it's how vulnerable are we? How much are we able to adapt and protect ourselves? How exposed are we? How much do we let housing be built right along the coast? How much do we let housing be built in zones that are forest fire prone and will become more so as the earth warms and certain areas dry? That's what risk is. So when you think about the risk related to this problem, always think about not just the physical side, but the human side. So keep that in your mind. How smart are we? How able are we to adjust? So this part is not from the IPCC report, but I think it's instructive. There was a report put out called Risky Business. It was done under the auspices of three strange bedfellows. Tom Steyer, who's the fellow who's billionaire hedge fund guy who's funding the pro-climate change side funded the pro-climate change side of the recent elections and plans to do so more in the future. Michael Bloomberg, the also billionaire former mayor of New York, and Hank Paulson, I don't think he is a billionaire, but he's a hell of a nice guy, I know him, and he's the former Treasury Secretary under President Bush. And they got together, they all think this is a bad problem that needs to be dealt with. They did a very thorough analysis of the impacts. One of the things they did is develop a new heat index. Heat kills. When there are heat waves, people die. They die in this country, they die more in greater numbers in developing countries, but the most startling episode of extreme heat occurred in Europe in 2003 when a heat wave killed about 40,000 people. Not just due to the direct effects, but also the indirect effects due to the combination of heat and air pollution. So it turns out that if it's very hot and very humid, you get a measure called the wet bulb temperature, which is a good way to determine actually how much you can stand the heat. And when the wet bulb temperature gets above 92 degrees Fahrenheit, people just basically can't be outside. They begin to die, and the reason is your body has a physiological limit. No matter what you do, except sit inside in air conditioning, there's a limit to how much your body can dissipate excess heat. So the combination of your metabolism and this extra heat on the outside can kill. And basically, when you get to 92 degrees Fahrenheit, not straight temperature, but this wet bulb temperature, which combines temperature and humidity, you get to the point where normal human activities outdoors, like walking, like farming, like construction work, like trying to take a vacation with your kids, is impossible, or at least potentially deadly. And so what they did is then look at the areas, if you got 100 years from now, or even 200 years, they looked way far forward, what areas in the United States would be reaching those deadly wet bulb temperatures. And the way, if you just go to the last couple of decades of this century, you get at least 1 week of the next most, let me just go back, page down, let me see, no, that's the other way. The category 3, which is called extremely dangerous. Those are the kind of temperatures that occurred in the last deadly heat wave we had in the United States in 1995 when 1,000 people died in Chicago. So though you get at least a week of that heat, not just in one place, but generally throughout the eastern United States, if you notice the yellow and red stippled areas. And some of those areas, in fact, about a third of them, get that temperature for several weeks, approaching a month. This is the left-hand panel on the top. And the number of places that get the category 4 heat, which is you go outside, and to caricature it, you go outside, you're dead. It's not quite like that. You go outside and you move around too much and you could die. It's at least one day every year in most of the eastern United States. But again, over a considerable fraction of that territory, it approaches a week of those deadly days. And then if you go to the next century, you get most of the summer in the eastern half of the United States as category 3, and a full month as category 4. Now, when I was at one of these IPCC meetings and we presented this information, we had sort of buried it in the bowels of the report because it's new and we were not 100% confident in it. This is one of the few cases where the government said, we want you to headline it, put it right up front in the summary. This is very important to us. We can't let that happen. It was an extraordinary moment, really. So that's heat. Another big effect is, as I mentioned before, the effects on crop yields. Crop yields have already started to decline. That is, the rate of growth of crop yields has started to decline. And that's very important because the human population is still increasing and will increase at least to the most optimistic projections until the second half of this century, probably longer. And people are what I call eating up the food chain. People in formerly poor countries that are newly, their economies in transition, they are newly relatively wealthy compared to what they were. They're moving to our slovenly diets and eating more and more meat instead of eating the grains that the cattle fed on, and that's making the whole system less efficient, means you need more grains. The net effect of that is that, so that's the demand side. More and more demand is what we would project. On the supply side, in fact, crop yields have stopped growing in some places, and their rate of growth has slowed in other places. That's for two reasons. Number one, the technological benefits of the green revolution have run out pretty much. And number two, climate change is adding a headwind. Climate change is knocking several percent off, depending on where you are, off crop yield growth. And the combination of those two effects is now threatening to put the demand for grain above the supply for grain. What'll happen? At first, not much will happen here. Your food prices will go up. People in poorer countries won't be able to afford to buy into the international trade in grains anymore. There'll be more malnutrition. Starvation will become somewhat more common. But as time goes, we thought that we were buffered against this, but one of the key findings of the latest report is, in fact, this is a problem for us too, that when you get to the higher warmings globally of 3 or 4 degrees, you get into terrain where food scarcity becomes an issue for us also. That's not now, it's not 30 years from now, it's toward the end of this century. It's something your grandchildren will have to worry about, maybe your children too, if we don't get this under control, And what this graph shows is that all the scenarios, scientists try to be fair, try to produce many futures with different estimates about how fast it's going to warm and how adaptation will work. We notice that some areas, the blue bars, are going to see increases in crop yields because it's warmer in the north, it's longer growing season, and higher carbon dioxide levels, that's a plant growth stimulant. But those, as the century goes on, as you see march from left to right, you tend to see the higher and higher bars, which are yellow, which means these are areas with decreased crop yields. So over the long term, the decreases well outrun the increases. And the final point I want to make on the impacts has to do with coastal flooding. As I mentioned before, as sea level rises, if a storm comes along, even if the storms are the same, because they're pushing a higher sea level, that sea level it pushes the sea inland to places, those storms push the water inland to places it's never been before. This flooding effect is why when you get a storm like Hurricane Sandy and you get a flood coming inland, Sandy, which was uniquely strong, pushed it to places we hadn't seen the water before. But in addition, it was pushing a higher sea level. Sea level around New York City is a foot higher than it was 100 years ago. It's worse than the global average. That's another reason why we got so much flooding. Well, the question is, what's the multiplier? In other words, if Sandy was about a once in a 1,000-year flooding event, in the future when we have higher sea level, how often will that kind of flood happen? Instead of happening once in every 1,000 years, this multiplier thing, the colors and the dots indicate the multiplier, and you see these astounding multipliers around almost every coastline globally where it's been assessed, and they run into the yellow to red end of that spectrum. They're getting multiplied by factors of 100 to 1,000. What that means is a storm like Hurricane Sandy, instead of happening once every 1,000 years, as many scientists think it would have happened naturally, they happen every 10 years. Now, New York City has barely totally recovered from Hurricane Sandy. What happens if we're in a world where a storm like that creates floods like that, instead of rarely, less than once a century, maybe even once a millennium, once every decade? And then other storms, which are not quite that as damaging, come more frequently. For instance, the 100-year storm, which itself can create a lot of damage, might happen in this area once every year. It's really a troubling thing to think about, and it's why one of the key reasons why we need to bring this problem under control. Now, in the interest of time, I'm not going to show you that one. If you took all these 3 risks and all the others that have been discussed and analyzed, like the risks to ecosystems, the risks to the global economy, the risk of something really bad happening, like one of the big ice sheets disintegrating fast instead of slowly, that is over the course of a couple of hundred years instead of a couple of thousand years. And you aggregate those risks, you can put them in different categories. The left hand, and that's these bars. The left-hand bar is threats to ecosystems. The next one is the risk from Sandy-like big extreme events. The third is the risk, basically it's the risk of food availability in developing countries. The fourth is the cost of the global economy. And the fifth is the risk of these big events like the loss of an ice sheet. Purple means big impact, very hard to adapt to, really high risk. Yellow means we're just starting to see the temperature which we'll start to see the effect. And red means it's the danger zone. And you can see the scale of temperature above pre-industrial levels, which is on the right there. You'll see that 2 degrees is pretty much where these risks really start to become near or well into the danger zone, no matter which risk you choose to be worried about. You know, some people will worry about butterflies. Other people will worry about sea level. If you live in Kansas, you might not worry about sea level. Others will worry about the whole picture, all of the bars. Well, this is why governments pick 2 degrees, because that's where these risks pile up, no matter what you're worried about. And so the question becomes, what do you do to avoid 2 degrees? That's the danger zone. This is another one of these far too complicated graphs, which I like to show because it shows you, again, the difficulty of communicating these issues. But basically, if you just take the 2 degrees and you go across to the right to that brown patch, that shows you what level of carbon dioxide in the atmosphere corresponds to that temperature. And if you go down then to this other thing, a panel on the bottom, it shows you what emissions reductions you have to get to keep at 2 degrees, what emissions reductions you have to make over the next 50 years. And you'll see then that if you want to stay in the 2 degree level, you have to be at concentrations around 450 to 500 parts per million of carbon dioxide. We're already at 400 parts per million. And that means we need cuts of around 50% between now and 2050. And that's why the announcement a couple of weeks ago about the China-US agreement was so important, because although it won't get us there, it means that the first meager steps in that direction are starting to happen. And you can see that on this graph. The smear of very dark green, I know I just got out of the camera lens, so too bad. The smear of very dark green are trajectories which would do that turnaround and start us on the path soon. It would mean China does what it agreed to do, to topping out its emissions in 2030 and then starting down. US and Europe already starting down. We'll keep the momentum open up. Other countries, and India is the next one to look at, Brazil, that they'll start moving their emissions down so that global emissions peak sometime in the period between about 2020 and 2025 or just thereafter, and then they start going down. That's one choice. And if we do that, we would have then the middle panel shows you what that implies. It implies emissions reductions of about 3% per year. That's a tall order. It's a rapid rate of emissions reductions, but it's not unprecedented at the individual national level, so we think it can be done. But if you stay on the business as usual curves, which are the light green set of curves going straight up in the left-hand panel, and then later, after 2050, after 2030, you decide you want to act, so you've delayed action, then your rates of emissions reduction have to be the right-hand bar in the middle panel, which are like 6% per year. There is no precedent for reducing emissions that fast from big economies. So if you want to gamble that some genius will produce a technology which will allow us to do that in 30, 40 years, you can gamble in your head, but don't gamble with my planet, is my view with that. The far more prudent thing to do would be start the emissions reductions immediately. This one you don't have to care about. This is the final message I'll leave you with. No, I got one more message after this. We have been burning carbon at high rates for about 150 years, exponentially growing rates, a little more than that. We had 790 gigatons of carbon, that's the full pie on the left, which we could burn if we were in 1850 thinking about it, knew enough to think about it, to avoid 2 degrees. We've already burnt 2/3 of that. That's the green on the left-hand slice of pie. And we have remaining 1/3 to avoid the 2-degree limit. So the question is, how do you slice up that 1/3, which isn't much, between countries in order to get a viable political agreement that this ought to be done? And again, the U.S.-China agreement of a few weeks ago is a good step in that direction. And just a final note, this pair of pictures haunts me. The lower one is we had a 100-year storm and a 100-year flood, I should say, in New York City and much of the Northeast coast in 1992. And this is a picture that was taken in the Hoboken PATH station, the Hudson Tubes. It's the subway that goes between New York City and northern Jersey. And the station flooded at that time because nothing had been done to prepare to keep water out of the subway system, and water seeks its lowest level. And the reason I remember this so vividly is a friend of mine was stuck in the station and had to run for his life. And you can imagine, it's like a horror movie. You go to leave the station, this torrent of water is coming at you down the stairs. After that storm happened, there was a lot of planning done in New York City and Long Island and New Jersey to try to keep this risk from eventuating again. There were plans to have temporary sealing of the subway tunnels when a storm like this was going to come. There were plans to raise the subway entrances. If you go down to New York City, there are these air vents all over the sidewalks. Well, water goes right into those. There were plans to raise and change the ventilation system so they couldn't be penetrated. Almost none of it was done, and as a result, when Sandy came around, that's the upper panel, same station in 2012, 20 years later, same flood. We forget. We always forget after one of these bad events. We forget much too quickly. And because bad storms don't come around in any particular area that often, we just sort of never seem to learn. Well, this time maybe because Sandy was so bad, there is some indication that efforts are being taken. I don't know. Let's come back in 5 or 10 years and see how much has been done. But this is the real threat, the real problem with global warming policy. It's a little less, how do we get the technologies to solve the emissions problem? Because we either have those or they're coming. Big progress recently, for instance, in solar photovoltaic cells. What we don't have, apparently, is the good sense to do the things, even the relatively simple things, to protect ourselves from the next bad storm. Thank you. What I showed are the global numbers. If you looked at the US, the numbers are a little different, but not that much different. The power plants are about 40% of emissions. They may be down a little now because of the switch to natural gas, which is a lower emitting fuel. And also what that showed is total greenhouse gases. It wasn't carbon dioxide, so the numbers are a little different. For the US, transportation the whole transportation sector is more like 25%. So individual family car, you add it up, it's about 18, 19%. These numbers are, again, it depends on which gas you look at, which country you look at, and they're also changing as we stand here because the energy system is in a bit of a revolution with cars getting much more higher fuel economy, which means lower emissions, and the power plants switching over from coal to natural gas, which means somewhat lower emissions.
Mike, I had a question. I don't know if you covered it early because I came in a little late, a little traffic on 287. Did you talk about the impact of CO2 on ocean systems at all and productivity?
That's an excellent question. Thank you. One thing I did not mention is that carbon dioxide dissolves in seawater. It drives the seawater to a state of higher acidity, there are many, many, many important shell-forming creatures in the ocean, particularly at the base of the food chain, well, just above the base. And those creatures will, in the future, have a harder time forming shells. There's a lot of uncertainty about how high these CO2 amounts in the atmosphere need to get before you actually cause one of these major species populations to collapse. But one of the early sensitivities is coral reefs, which are already under threat because they're sensitive to higher temperatures. There, the combined threat of higher temperatures and a more acidic ocean is a very, very fundamental threat to their viability when you get in the range of a degree or two over pre-industrial temperatures. So it's a big deal. We're learning more about it all the time. It's not encouraging.
Hi, thank you for your talk. It was excellent. And I have a question related to modeling. For many years, scientists have said, and currently still say, you can't tie any particular event to climate change, but we can see what the trends are. But recently, it seems like there's been some studies, some modeling to show that you can, for example, in Australia, the heat waves or drought there, several models have showed they are a result of climate change. And I'm wondering what you think about this new approach or new ability. Are we arriving at the point where we can connect those two dots?
Excellent point. For years, we couldn't connect individual events to the buildup of the greenhouse gases. But starting with the 2003 heat wave in Europe, and then followed by the 2010 heat wave in Russia, scientists rather convincingly were able to say what fraction of that heat or how the extremity was changed by the buildup of the greenhouse gases. And now that same type of modeling can be applied with lesser certainty to some droughts, and in the future, maybe 5 or 10 years out, to tropical cyclones, hurricanes. We're not there yet. And it can already be tied to some extent to the damage caused by storms along the coast, because we can say with some certainty how much of the sea level rise was due to the buildup of the greenhouse gases and the resulting warming, and therefore we can say how much of the damage of a storm from a hurricane like Hurricane Sandy would not have occurred had sea level been the same in now as it was in 1900, say. So for instance, New York City, about the buildings, I always get my fact a little screwed up here, but I think the number was that the buildings equivalent to the residences of 50,000 people would not have been, that were flooded, would not have been flooded if that the sea level had remained where it was 100 years ago. So yes, this is the cutting edge of science. We're getting better at it. The progress will be continuous and I think very rapid.
Excuse me, it just seems to me from, if I understood correctly what you're saying, from the presentation, that really business as usual is not compatible with any serious efforts at mitigating this particular problem, which really leads to only one conclusion, it seems to me, and that is we've got to stop worshipping at the altar of economic growth. And I don't see any of the major reports from either the UN or the IPCC or any of the major politicians anywhere in the world that has really taken the serious move of asking for at least a steady state economics.
Yeah. So that is a commonly held view. I myself don't quite agree with it. I think that there's a fair distance, a good distance we can go towards where we need to go with improved technology. But the reality is that as you get later in the century, we will need changes in lifestyle. I don't know if they translate into lower economic growth. They may simply translate into different ways to measure economic growth. And through a combination of technological change and people adjusting the way they live, we can avoid a dangerous warming. And you see some hints of this already, because energy prices have been relatively high in the last 15 years, particularly oil prices until very recently. It's well established that young people tend not to drive as much. They tend not to buy cars because they can't afford them. They can't afford the fuel. Economic times have been tough. They tend not even to get driver's licenses. They tend to want to live more in centrally concentrated areas, cities, large and medium size. That, if that continues, that will eventually lead to a monumental change in the settlement pattern in the United States. Does that mean that, you know, things are worse, things are better, more or less economic growth? I don't know how to answer it. I do know that it would make it easier to solve the greenhouse problem. The political difficulty in having that conversation, which is why the governments don't talk about it, is because the developing countries, quite rightly, want to develop in much the way we did so they can haul themselves out of poverty. And it's easy for us to say we want to avoid a greenhouse effect, which is going to be a disastrous problem in 50 years, when they've got people who are malnourished day in and day out. So what I think everybody who thought about this hard is hoping for is that there's some way to thread the needle between having to just sort of stop economic growth and reaping the benefits of lifestyle change and technological progress to yet let humanity get to an improved state of existence. If it comes down to a world where we have to stop economic growth as we know it or solve the greenhouse problem, I can tell you we're not going to solve the greenhouse problem.
Question, since somebody brought up the oceans. I remember reading speculation that one of the knock-on effects of this whole thing may be that the Gulf Stream might be negatively impacted, which would obviously have a huge effect on the climate of Northern Europe. I mean, to a certain extent the U.S., but much more them. Is that still the case? What's the current thinking on that?
So the circulation that the Gulf Stream is part of, called variously the Thermohaline Circulation or the Atlantic Meridional Overturning Circulation, transports heat and salty water from the tropics to the north, where it sinks and forms a sort of conveyor belt circulation, which oddly comes up in several places, but including all the way across the world and in Antarctica, near Antarctica. And if that circulation were to slow, as it has under natural conditions in previous epochs long, long ago, it could create an extreme cooling in parts of Northern Europe. Now, at an earlier time, it was thought that that would kind of like bring a mini ice age to Northern Europe. That's not the case, because that would only happen if there's enough warming to cause this change in circulation. And what you get over most of Europe is a cancellation between too much warming and some cooling. So it has the effect of damping the warming rather than bringing on an ice age. But I've looked at the numbers. For some places like Scandinavia, it's a raw deal. Plus, there are other things that happen that reverberate in the climate system, which cause problems sort of hemisphere-wide. What we know will happen is that circulation we expect it to gradually slow down as the world warms. But whether it slows down to a point of this total collapse of the circulation, at this point, it's a disfavored outcome, let's put it that way. Science has changed a bit on it.
I'm wondering if you or your colleagues or the policymakers you talk to ever feel hopeless when discussing these issues, and if so, how you address that. Basically, I'm looking for a more hopeful, constructive way of discussing climate change with my colleagues, and I'm wondering if you can give me any of your insight on that.
Yeah, I mean, you'll never find an elected official who'll feel hopeless. They'll instead say they don't believe the problem's happening. I've talked to a lot of policymakers at all levels over time about this. And in general, their reaction is sort of, look at what's the next steps in front of us. Don't think so much about if you think about the big picture, if I think about the big picture, it's too much, it's too daunting. You think about what are the next steps. And I think they're pragmatists. That's why they got into office in the first place. And so they think about what can we do in the next 5 years, 10 years. I've met President Obama once before he was president and shortly before he announced when he was a senator. And that was the way he was. It was like pragmatism. Tell me, so what can we do next? What can we do about coal? What can we use corn-based ethanol? Because he was from Illinois, it was a corn state. Illinois is big on nuclear power. Can we use what will nuclear power done? What are the other options? It's very much a transactional thing. Show me what I can do. And I think that's the attitude. I've never seen a politician really despair. Even Al Gore, who is absorbed in this problem by far more than many scientists who work on it. I never saw despair out of him. I saw annoyance, frustration, but not despair. You can't afford it. What's the point?
Thank you so much, Dr. Oppenheimer.
Thank you.
For those of you who had questions that you were really hoping to ask Dr. Oppenheimer, we have a reception right now happening in the tutor room. So we hope you'll come join us there, continue the conversation. We're so grateful to the Environmental Law Program for helping us host today, and to the Pace Energy and Climate Center. Thank you all for coming. It was nice to have you here. Thanks.